Hi, and welcome to this plenary session, From Production to Consumption, Solutions for a Circular Economy. I'm Miranda Gorman, Senior Research Fellow for Industry here at Project Drawdown, and I have with me several experts to teach us about various aspects of the circular economy and industry. We at Project Drawdown have investigated the efficacy of a number of solutions related to the circular economy, including alternative materials, waste management, industrial processes, and we've seen a significant potential for climate change reversal. In fact, we identify that 21% of emission sources are directly related to the industry sector. This sector includes solutions related to improving global circularity from a number of different approaches, such as production of materials from alternative feedstocks instead of extractable non-renewable resources, as well as responsible waste management that prevents the loss of material resources to landfills or dumps, as well, and including improvement of industrial process efficiencies. Currently, all of Project Drawdown's industry solutions fall into three clusters: using waste, addressing refrigerants, and improving materials. All of these activities contribute to a more robust circular economy and move society farther away from a linear extract, consume, dispose model. I'm going to share with you some more information about our latest results from the Drawdown review released earlier in 2020, as well as some of our upcoming work. Before I do that, though, I want to introduce my panel of experts who can give us some more information about the widespread benefits and implications of circular economy solutions. Yoni is here, who leads SYSTEMIQ's global modeling efforts of ocean plastic leakage and their findings regarding the plastic circular economy. Silpa Kaza from the World Bank, who is the lead author of the What a Waste report on the state of waste management and opportunities globally. Senorpe from Penn State is here to talk about specific applications of agricultural waste and opportunities for circularity there, as well as Maxime and Durwood from IGSD to talk about their work in refrigerants.
Good morning. It's a real pleasure to be here today to be talking about breaking the plastic wave, a project I've been working on for the last 2 years. It's been a baby of mine, and I'm thrilled to be sharing it with you all today. My name is Yoni. I'm with SYSTEMIQ, and we are a B corporation headquartered in London with offices in Munich, Jakarta, Amsterdam, and Sao Paulo, with a mission to drive system-level change in critical environmental and social systems. So why did we spend the last 2 years building a flow and stock model to understand the global plastic system and the environmental and social and economic implications of different actions? To me, it all started in my first trip to Indonesia. And as you can see in the picture, the beach was covered in plastic as far as the eye can see, 80 centimeters high. I remember walking on the plastic, feeling that squishiness of the plastic, and children playing on plastic, probably not even aware that there is sand underneath. And if you look at the global debate on plastic, there are unreconciled propositions. Some people are saying that we just need to ban plastic. Some people are saying that we need to recycle plastic. Some people are saying that we need to burn or bury plastic. Some people are saying we can clean up after the fact. And some people are saying that we can turn to biosolutions. But the reality is that we have very little data in terms of what are the economic, environmental, and social implications of each of these solutions. What geographies or materials would they apply to? What costs or timelines are involved? In short, the world doesn't have a strategy to deal with ocean plastic pollution. And for that reason, SYSTEMIQ, together with our partners at the Pew Charitable Trusts, set out an initiative to build a global roadmap of solutions to better understand how the world could tackle with this global challenge. And what we found through our modeling work is that under business as usual, by 2040, we will be producing 2 times more plastic than today. There will be 3 times more leakage to the ocean and 4 times more stock of plastic in the ocean. That is 2x, 3x, 4x by 2040, certainly a future that none of us wants. What we also found is that there is no silver bullet. Any of the solutions on their own will not solve the problem. If you try to scale recycling as ambitiously as you can possibly imagine, scaling collection, and designed for recycling and mechanical recycling and chemical recycling, all these solutions focused on recycling, you'll barely bend the curve. You will not get leakage onto zero. And also if you implement only upstream solution, just by banning or substituting plastics upstream, you will not solve the problem. However, I do have some good news for you all today. And that is that we have the solutions to address 80% of the leakage. That's right, we can reduce 80% of the leakage by 2040 with known solutions. And that does not require us to go back to the Stone Age or to have aliens from Mars bring solutions. This is all with known solutions, known technical solutions that we know and understand, and within economic, political, social, and climate constraints. In this chart that I'm showing you now, that we call the wedges chart, this is the roadmap that we have painted, and this is the portfolio of solutions that we believe could, in combination, address the plastic challenge. And I won't take you through all of this detail, but the key message is that we need to combine upstream and downstream solution. We need to roll out all known solutions concurrently, simultaneously in all the countries and starting immediately. If we do that, we can reduce ocean plastic pollution by 80%. And that solution, that scenario that we call the system change scenario, also reduces greenhouse gas emissions, reduces costs for the public sector and for the private sector, because it leverages circular economy principles that have all these benefits. To hear more about Breaking the Plastic Wave, feel free to Google Breaking the Plastic Wave, and you can see more information about our research. Otherwise, I hope you've enjoyed it. I would now like to hand it over to Silpa Kaza from the World Bank, who will talk more about waste. Thank you and enjoy the rest of the conference.
Hi, everybody. My name is Silpa Kaza, and I'm a senior urban specialist at the World Bank. I'm really excited to be a part of this circular economy event today. And I'm going to bring the World Bank perspective, which is kind of working more in low and middle income countries. And we work across the entire value chain for waste management, as well as, thinking about sector reform and financial sustainability and social inclusion and other aspects. So when we're thinking about circularity, you need to have a foundation of an integrated waste management system, right? You need to have a collection system in place, a way to aggregate the waste, a way to manage it in a safe manner. And then we can start talking about, having materials be inputs into the broader circularity process. So keeping that in mind, and given that, a lot of our work starts with building waste collection systems, I'm going to talk about the main findings of a publication that we put out called What a Waste 2.0, where we collected data on waste globally. So I'm going to talk a bit about global waste management trends, so you have a sense of where we are right now. The three main messages that I would love for you to walk away with today are, first, that we're expecting waste to increase by 70% by 2050, with most of the growth happening in sub-Saharan Africa and South Asia. And this is actually more than double population growth over the same period. Second, about a quarter of our global plastic waste from municipal solid waste is coming from the East Asia and Pacific region. And having a more circular approach is obviously necessary for sustainable development. And third, about half of our waste operations involve the private sector, nonprofit, or civil society. So there's plenty of room to engage. So in 2016, we estimated that we were generating about 2 billion tons of municipal solid waste. And by 2050, we're expecting to generate about 3.4 billion tons. Waste generation is positively correlated with urbanization, which is why we're seeing that in sub-Saharan Africa and South Asia, waste is expected to grow the fastest. So in sub-Saharan Africa, we're expecting waste to approximately triple, and in South Asia, approximately double. Per capita waste generation increases with income, which is why we see that high-income countries generate about 1/3 of the world's waste, with only 16% of the population. And on average, we generate about 3/4 of a kilogram per person per day. But you can see that there's a really large range depending on what region you're in. So in sub-Saharan Africa, it's less than 1/2 a kilogram per person per day. In North America, it's more than 2 kilograms per person per day. And we see that the composition of waste varies by income. So in high-income countries, we tend to see more dry waste or recyclables proportionally. So about 1/2 of waste in high-income countries tends to be dry waste or recyclables, with less than 1/3 being organic waste. But then in low-income countries, we see that more than 1/2 is organic, and only 17% tends to be recyclables. But of course, this is proportionally. And I included photos of food waste and plastic waste, since those are two very important waste streams. So when we're thinking about food loss and waste, that amounts to 30% globally. And in terms of plastic waste generation, we're estimating that we generated 242 million tons in 2016 from the municipal solid waste management system. And if you're having trouble visualizing that, we wanted to break it down a little bit more. So it's about 24 trillion plastic bottles, or 4.8 million Olympic-sized swimming pools. And really, it's 3 regions that account for 60% of the plastic waste generation: North America, Europe and Central Asia, and East Asia and Pacific. We see that in low-income countries, only 39% of waste is collected. So you can see that, this is really the starting point. And in high-income countries, there's nearly universal waste collection. About 1/3 of the waste globally is openly dumped or burned, but in low-income countries, it's actually more than 90%. And so if you recall the previous slide, I said about 40% of waste is being collected, but overall, more than 90% of waste in low-income countries is being dumped or burned. So there's a huge discrepancy even there. Solid waste management contributes to about 5% of global emissions, just considering the kind of how you choose to manage the waste. And the poor are the most affected by inadequate waste management. So whether it is because people's livelihoods depend on the sector, waste is dumped by their communities, or the communities don't even receive waste collection services, they're disproportionately affected. And vulnerable populations tend to be a part of the informal waste sector. So migrants, children, women, the elderly. And just to give you 2 numbers, in Cairo, there are about 96,000 waste pickers, and part of their responsibilities are providing 10% of the city's collection. And in Dhaka, there are 120,000 waste pickers, and 90% are female. 30% of countries do not have any institutions or policies to address waste. Waste is predominantly a local government responsibility, but we see that local governments can only cover about half of investment costs for their waste systems, and then they face the real challenge when it comes to operational expenditures. More than half of services are operated by public entities, and about 1/3 involve a public-private partnership. In low-income countries, we see that waste management takes up about 1/5 of the municipal budget. And in high-income countries, it's about 4%. But again, I just want to point out that if about a fifth of the municipal budget is being taken up and there's 40% collection, but then more than 90% is being dumped, there's a lot of work to do. And of course, in high income countries, the cost is higher on an absolute, in terms of absolute value. So we really want all of this data to be a call for action. And I'm just going to flag the areas that I had mentioned up front. So again, first we need to focus on sub-Saharan Africa and South Asia, where about half the growth by 2050 is coming. And also in these regions, more than 2/3 of the waste is currently being openly dumped or burned. So we really have to get ahead in order to prevent any further crises. Second, we need to prioritize the 5 countries in Asia to address the bulk of the marine litter problem. Third, we need to have the right regulations and incentives in place to attract financing and the right partners, whether it's civil society or the private sector or nonprofits, to make sure that we're able to deliver. And finally, we need to work with all stakeholders to work towards a more circular economy. So manufacturers, citizens, governments, operators, everyone has a role to play. So with that, thank you very much. If you go to the website on the screen, you can access all the data as well as the publication. And thank you again for inviting me. So now I'm going to hand off to hear more about agricultural waste from Senorpe.
Hello, I'm going to talk to you briefly about renewable natural gas production and related carbon capture and storage potential in the general context of circularity with a specific case study from Pennsylvania. My name is Senorpe Asem-Hiablie. I am a Drawdown research fellow and also at Penn State University as a KC assistant research professor. Why renewable natural gas? Direct relationships have been observed between fossil fuel derived atmospheric carbon dioxide and planetary warming. There is a need to reduce cumulative emissions to near zero by the end of this century, according to IPCC's estimates in 2014. Now, stabilizing the Earth's atmosphere, the Earth's temperature to below 2 degrees Celsius of pre-existing levels would also require that emerging technologies and pathways mature to produce and use high-end biofuels as energy. These technologies are also will help greatly reduce methane and other greenhouse gases emitted from organic waste. Renewable energy sources offer localized and cleaner alternatives to conventional fossil fuel combustion using existing natural gas grid or other forms of conveyance. Renewable natural gas is a biogas that has been purified, making it interchangeable with fossil energy. There are 3 ways that renewable natural gas reduces greenhouse gas emissions. One is that it is cleaner burning. Renewable natural gas is identical to fossil natural gas, and is cleaner burning than diesel. Methane, which has 34 times more global warming potential than carbon dioxide, can be captured and used. Otherwise, it would have been harmful when left into the environment. So these harmful gases are potentially harmful gases, are turned into beneficial use. Carbon dioxide capture and storage also is possible from the co-produced carbon dioxide during the biogas production process. As you can see from my diagram, there are both agricultural, non-agricultural, and domestic sources of waste that could be pulled together for RNG production. Here are some of the pathways for renewable natural gas production. Several exist around the world, but in the simplest form, we can get renewable natural gas from purifying biogas, from wastewater treatment plants, from landfills, as well as from the agricultural sector in the form of manure, crop residue, perennial gases grown on degraded land, and waste and byproducts, all being anaerobically digested, as well as through thermal gasification, which is also another process to produce biogas, which will eventually be purified to give us renewable natural gas, which in some areas where the natural gas grid exists can be directly pumped into the gas grid. During the anaerobic digestion process, we have liquid effluents and solid effluents, all of which can be recovered, the liquid part being used as irrigation, or the solid part being transformed into biochar, fertilizer, bedding, or compost, which all then go back into the agricultural sector, closing the loop. Talking about Pennsylvania, as I have mentioned previously, we did an inventory of potential feedstocks across the states that could be used for RNG production. And you can see from this map that they are spatially distributed with unequal access to natural gas infrastructure. This therefore requires that we need to examine various scenarios for minimizing costs. This could include establishing virtual pipelines or centrally locating digesters, and from which we can pull the feedstocks and distribute them from there, distribute the products from there. We are also looking at addressing this question using a co-digestion optimization model for RNG production and carbon capture and storage in order to minimize total costs. Built into this co-digestion model are federal and state level incentives to make all these economically feasible. This map shows briefly some of the geologic carbon dioxide sequestration potential in Pennsylvania. This does exist. However, we need to be careful in how this carbon is storage. So technologies that are developed need to be developed safely in addition to other requirements to reduce carbon emissions. I also like to mention that key considerations for this solution in the form of RNG production are feedstock selection, the storage, transportation, conversion, and pipeline distribution. We need to consider economy of scale and as well as the how that relates to variable costs and operations. That relates to variable costs and capital costs. In the local and regional context, the feedstocks do exist in most places in the form of agricultural and non-agricultural waste. They need to be used scenarios in form of, is it going to be used directly as transportation fuel or pumped into the natural gas grid? The options for carbon capture, apart from storage, if storage does not exist, are also needed. And the economic feasibility from incentives are also needed because this is a maturing technology. Thank you. Now I'd like to hand over to Durwood and Maxime from IGSD, from who you'll be hearing about refrigerants.
So I'm Maxime Begard, a French lawyer for the Institute for Governance and Sustainable Development, IGSD, for which I've opened the Paris office. And I'm joined by Durwood Zelke, president of IGSD. So Durwood, tell me a bit more about the science behind the climate emergency.
Thank you, Maxime. The best scientists who focus on the climate emergency, such as Tim Lenton at Exeter University, tell us we have between 0 and 10 years to slam on the brakes of warming. Otherwise, the self-reinforcing feedbacks will take over. The Earth will warm itself beyond human ability to control the climate, and will pass potentially irreversible and potentially catastrophic tipping points. An illustration of the feedbacks is what's happening in the Arctic. The Arctic is warming at 3 to 4 times the global average right now, and that's causing the melting of the land-based snow and the sea ice that floats on the Arctic Ocean. And as we lose that great white shield that now sends incoming solar radiation safely back to space, we will let it enter into the darker ocean and land and accelerate the warming in the Arctic further. When that happens, it'll melt even more of the ice, and that'll cause even more warming. That cycle of feedback loops will also start melting permafrost. It's already melting, but it'll accelerate the melting of permafrost, which stands for permanent frost. It's no longer permanent, it's melting. And when it melts, it releases ancient stores of carbon dioxide, N2O, and methane, 3 powerful climate forcers or climate pollutants that further accelerate warming. So it's another feedback loop. It starts a wicked cascade that goes throughout the entire climate system of the planet. Another illustration would be the Amazon forest. So we've destroyed right now about 17% of the Amazon through burning, through cutting for agriculture principally. And when we lose somewhere between 20 and 25%, lose is not the term, but destroy, what will happen is that the Amazon itself will warm enough to destroy the remainder 80 to 75 to 80%. So this is, again, what happens when a feedback loop takes over. When you lose the rest of the Amazon, you lose each incremental piece, causes more warming, you lose more warming, you lose more until it's gone. And because the Amazon regulates so much of the weather of the entire South American continent, you're going to have droughts throughout and floods in other places, and it's going to be hell on food production. And it's going to be another one of those tipping points that the world may not be able to survive. So we have, as I said, somewhere between 0 and 10 years. Let's think of it as a 10-year sprint to 2030 that we must win on the way to 2050. In this sense, 2030 becomes the new 2050. You've heard a lot about the 2050 goal, net zero emissions, very important. The world's doing a pretty good job committing politically to that distant goal, 30 years hence. But if we don't win the 10-year sprint, it won't matter what the 2050 goal is, because we won't be in the race after that 10 years if we lose control because of the feedbacks.
Well, yes, pretty clear. Thank you. And we know who are the sprinters. So the sprinters are the so-called short-lived climate pollutants, methane, black carbon, tropospheric ozone, and the refrigerants HFCs. We know that if we cut the refrigerants, the super climate pollutants, short-lived climate pollutants, we could avoid 2 to 6 times more warming than just cutting CO2s. We also know through the IPCC 1.5 report what we need to do. So to zoom in on the HFCs, the parties to the Montreal Protocol adopted in 2016 the Kigali Amendment. Through this amendment, we could avoid 0.5 degree of warming towards the end of the century by phasing down HFCs. But this is only part of the problem. We also need to look into improving the energy efficiency of the cooling equipment. And by doing so, we could all double the climate benefits of the Kigali Amendment. So we need to look into the right metric, the metric to select the right alternative refrigerants. And this metric is the life cycle climate performance metric, there's the right one to choose the alternative and the technologies on the refrigerant front and in the cooling sector. So we have a pathway, we have the sprinters, we know where they are, we know what to do. And I think, Durwood, you can join me in concluding that the whole climate community needs to engage with this new rhythm, the need for speed. This is the only way we can safely get to 2030, right?
You know, Maxime, you're absolutely right. The world's leaders do not yet fully comprehend what the climate emergency is really about. The youth movement does understand this. Groups like the Extinction Rebellion, they understand it. A group of scientists understand it. But it is potentially catastrophic for civilization. We enter the hothouse Earth that the climate scientists have predicted. So yes, it's absolutely essential to focus on winning the 10-year sprint. If we win that sprint with the short-lived climate pollutants, as you just articulated, cutting the HFCs through the Kigali Amendment to the Montreal Protocol, cutting methane, and maybe we need a new methane treaty. That's a possibility, but we have to cut methane aggressively as well from oil and gas sector, from landfills, and from agricultural sector. And then black carbon and tropospheric ozone. Black carbon is an air pollutant, and the world should be cutting this for health reasons alone. It's also associated strongly with higher death rate from COVID-19. If you are unfortunately living in a highly air polluted area, you will be more likely to die from COVID-19. You also, I know you're based in London at the moment, and in London we just had the coroner declare the death of this 9-year-old girl to be significantly caused by air pollution. So, I mean, we are literally killing people. The World Health Organization says about 7 million people a year. So that should be sufficient motivation. It's not, but it should be for taking care of the black carbon. So when the world finally understands the true emergency, then they're going to turn to these fast mitigation measures. They're going to put the sprinter into the race. And if we win that, as we can, in the 10-year sprint to 2030, then we're going to have a chance to make it to 2050 and the net zero emissions.
Great. Well, I think, you know, there's a need for speed, as we've said before. Thank you all.
All right. Thank you, Maxime.
Thank you so much to all of our expert speakers. It's really exciting to hear more about the cutting edge work being done in all of these areas. It's really clear to me that our current linear economy needs a lot of improvement in a vast range of areas. We're thrilled to be able to hear from people doing that work who can highlight the importance of commitments to a circular economy. Improving the circularity of plastics can have vast and far-reaching impacts on climate as well as our ocean ecosystems. Waste management provides opportunities for equity and better living in developing regions, and agricultural waste can clearly be used to produce energy as well as other necessary resources. Preventing linear use of HFC refrigerants can have profound immediate effects on our climate. As I briefly mentioned, Drawdown has done significant research focusing on the climate change impact of industry solutions. From the Drawdown review released earlier in the spring, we looked at 2 scenarios for all of the solutions listed here: alternative cements, bioplastics, composting, recycling, recycled paper, waste to energy, landfill methane capture, methane digesters, as well as refrigerant solutions. What you're looking at here are the potential emissions reductions for all of these solutions in gigatons of CO2. Clearly, refrigerants are a huge opportunity, netting over 100 gigatons together. But there are significant opportunities elsewhere as well in alternative materials and waste management. Now, I want to share with you some upcoming work to look forward to from Project Drawdown. We're focusing moving forward on restructuring some of the clusters of work. The first is thinking about limiting the system boundary of our waste management solutions to really just focus on end-of-life management to get a higher resolution view of what's going on in the waste management sector. This provides opportunities for new alternative materials models from recycled feedstocks, such as glass, metal, and plastic. Finally, we're also thinking about new industrial process models that are focused on production of end-use products and services for consumers and thinking about their entire supply chain. The white boxes you see here are brand new models that we're working on currently and will have results for coming in the next year. This new system provides a feedback loop between all of these clusters, waste, materials, and industrial processes, where the waste and materials models can provide feedstock limitations or be allocated to individual models to produce a higher resolution analysis and more accurate results. For example, the household and commercial recycling model will provide insight into how much feedstocks are available for recycled materials, such as recycled metals and plastics. Recycled plastics and bioplastics will also be informed by an integrated plastics production market. These materials might then inform the industrial process models, which will ultimately lead to estimates of waste production. Now, I have some really exciting news about our very first brand new industrial process model, sustainable clothing. This model takes a look at solutions to improve the sustainability of the clothing supply chain from raw materials production to consumer purchase. We look primarily at two levers of change: improved materials and improved processes. Some examples of improved materials are transitioning away from traditionally farmed cotton to organic cotton, which uses less energy, water, and pesticides. Additionally, replacing polyester with recycled polyester, or promoting the use of natural materials with lower impacts, such as hemp or jute or flax. The second lever, improved processes, includes solutions for higher efficiency machinery, heat capture and reuse, low water dyeing, and more. We do have some preliminary results to share from this new research. We estimate that by 2050, adoption of these sustainable clothing solutions, both better materials and improved processes, might range from between 7% to 56% of the market and have potential climate change impacts between 3 and 36 gigatons of carbon. These are really huge impacts and very exciting results. Thank you so much for your attention and for staying with us to learn all about various industrial process and circular economy solutions.